Hi everyone. So today I will actually go through problem L from week 4 Kattis set. So this question is one of the more challenging problems. Okay, so we will just go through it slowly. So this question, the description of this question is pretty short. Okay, it requires you to find the greatest number of people you can invite to dinner given a particular layout of a piece of land. So the land given comprises of only dots and crosses. Okay, so if you take a look at the first example, okay, if there's a dot, it means that the square is free. And if there's a cross, it means that that particular spot is blocked. So you need to find whether you can form a rectangle of the largest perimeter inside this grid. So for instance, if you take a look at this example, okay, so let me just draw out an example. So for instance, okay, so for example, if you have a piece of land, okay, that is comprises of this particular setup. Okay, so let me just give a random example. Okay, so for example, you have a piece of land like that. Okay, there are multiple rectangles you can form. So one example of a rectangle you can form is maybe just around one dot. So what is the parameter of this rectangle? The parameter is 4. Okay, that means you can invite a total of 3 friends. So this question says that you want to invite friends over to sit around the rectangular table, and it doesn't include you, so you have to minus 1 from that count. Okay, so in this case, you can invite 3 friends. Okay, but of course, you can form larger rectangles, such as maybe, for example, this rectangle, right? You can also form this rectangle. And what's the parameter of this rectangle? The parameter is 6, right? Which means you can invite a total of 5 friends. So this is quite big, but you can still form a larger rectangle, which is, you probably have realized, okay, this rectangle here. You can form a larger rectangle, and this rectangle has a parameter of 10, which means you can invite a total of 9 friends. Therefore, the answer for this question is 9 here, given here. Okay, so your job is given a grid. Can you find the most number of friends you can invite? In other words, you want to find the rectangle with the largest parameter possible. Okay, so let's take a look at the next sample input. So next sample input comprises of this figure. So let me just draw it out. So it comprises of this figure. Okay, let me just give an example like that. Okay, so if you notice, all the dots are separated. So the largest rectangle you can form is actually just like that. It can also be like that or like that. Okay, so all these rectangles have the same parameter. Each of the rectangles parameter is 4. So the best answer is still 4. Okay, but remember, it doesn't include yourself, so you have to minus 1 from this, and the answer will be 3. So you can invite 3 friends to dinner. Therefore, the answer for sample output 3 is 3. Okay, so the question is, how do you figure out this solution? Okay, how do you find the largest rectangle you can form? So this is a bit difficult. The first thing you need to know is how to solve a variant of such a problem. Okay, so before we go on to this, let me show you another problem, and we will solve that first before we move on to this problem. Because you need to know how to solve that problem first before you can solve this. So let me give you another problem. Given a land full of buildings, okay, so for example, you have many buildings here. Okay, you have many. So for example, I would say this is 4 meters, 6 meters, 1 meter, etc. Okay, so maybe this one is 3 meters. Uh, this one is 10 meters, etc. Okay, maybe this one is 8 meters. Okay, so given given the buildings like in a straight line, okay, you want to find the largest billboard that you can place covering the buildings. So the billboard has to be rectangular, and it cannot cover any empty space. Okay, so if you take a look at this, you realize, okay, there are many possible billboards that you can place, right? You can place maybe a billboard here. You can place a billboard here, right? And this billboard will have an area of, okay, it has an area of 2 by 4. So the area is 8, etc. But if you take a look, you realize you can actually form larger billboards. For example, you can form another billboard like that. Okay, and the area here is actually 9 because this is 3 by 3. Correct? So you can play around with it. You can try to figure out, is there any larger billboard I can place? Oh, you realize there's another billboard you can place like that. Like that. And this is 6 by 1. The area is 6, which is going to be smaller than 9. So the answer in this example, okay, is it 9? Now you think about it. Actually, no. There's a larger billboard I can place like that. Here. Larger billboard I can place. This is actually 2 by 8, right? So the area of this billboard is 16. So maybe this is the answer, right? But the question is, how do you figure this out? And what is the time complexity of the best solution you can think of? Okay, so let me just tell you what is the approach to solving this problem. Now, this is a very classic problem that requires you to use a stack. Okay, so what you need to do is that you need to figure out, okay, for every single rectangle for every single building in this input, what is the maximum area of a rectangle that you can form, given that that building is the one where the billboard covers. Okay, so let me just give an example. So what I mean, right, is that, for example, you have a few buildings here. Okay, so for example, you have a few buildings here. Okay, so what we need to do is that for every rectangle, you need to figure out exactly where, okay, it can extend its sides. So that in other words, for example, if I look at this first building, okay, this building of height 4, okay, now I ask you, okay, what is the maximum area, what is the maximum region that I can extend this side to without getting blocked by any building? So you realize the answer will actually just be to here, to here. Because I cannot extend it any further because the next building is shorter than this building. So therefore the billboard cannot go over this region because it will be covering an empty space. Therefore, you want to figure out what is the right boundary of this billboard that you can extend to the right of this building. Okay, in other words, this billboard can be extended to this portion. And for the left portion, you also need to do the same thing. How much can you extend to? There's no building to the left of it, so therefore it can just extend here. So why I do this is because this will tell me what is the largest rectangle I can form. In this case, the largest rectangle will be the distance between the right boundary and the left boundary. This will give me the width of this rectangle. And the height of the rectangle will just be the height of the building itself. Now let's try another example in case you're a bit confused. Okay, so let's try another example and you might slowly get a hang of it. So for example, let's try this example. Okay, 1, 5, 2. Okay, so now the question is, how much can you extend for this building of height 1? So that means you need to figure out your right boundary. Where can you extend to? You realize it can actually extend all the way to here, right? Then it cannot extend anymore because there's no more buildings to the right. And for the left boundary, it can extend all the way. It can extend all the way to here, right? So therefore, you know that this rectangle is just like that. And the area of this rectangle, okay, is the difference between the right boundary and the left boundary. That's the width of the rectangle, which is 5. And the height of this rectangle is its height, which is 1. So the area is 5. You need to do this for every single rectangle inside the input. And then you figure out what is the largest rectangle among all these buildings. Okay, this can be done in O(n) time. So the only way you can do it in O(n) time is to use a stack. Okay, so why do you use a stack? Okay, so let me explain why you can use a stack to solve this. Okay, so this requires you to use a stack. So let me show an example how you can do this using a stack. So for example, I have a few buildings. How a stack works for this problem is that, okay, you have to start off with an empty stack. And inside the stack, you store the index of the building. So this is very important. You have to store the index of the building. Why do I store the index of the building? Okay, that is because, remember just now, for every building, you need to figure out where is the maximum you can shift your right boundary and where is the maximum you can shift your left boundary. So where you shift the boundaries to, okay, will determine the width of the rectangle you are forming. Therefore, you need to know exactly which position you can shift your boundary to. So you don't need to store the height of the building itself. You need to store where that building lies in, so that you can obtain the position to where you can shift your boundaries in O(n) time. Okay, so that is very important. You need to store the index of the buildings. Okay, maybe you still may not understand this, okay, but as I go through the algorithm, you might find it easier to comprehend this. Okay, so let's say this is index 0, okay, this is index 1, this is index 2, this is index 3. So the first thing we will do is that we will have an array that will store, okay, the right boundary. Okay, right boundary. At the start, everything will be initialized to -1. Now, let's take a look at the first rectangle. So the first rectangle, okay, is a height of 5. Correct? Okay, but there's nothing in the stack currently. So we don't need to do anything. We just need to put its index into the stack. So I'll put index 0 into the stack. Okay, now I'll move on to the next rectangle. Okay, the next building has a height of 7. Correct? Okay, so now comes the interesting part. Remember, we are finding the right boundary. Okay, that means we are figuring out where can this right boundary shift to. Okay, so we are only concerned about the right boundary. Now, in this case, we just need to check, okay, if the top of the stack, okay, is larger than our current height. Okay, so why do we need to do that? It's because now the rectangle we are looking at is a height of 7 meters. But the previous rectangle in this stack has a height of 5 meters. So we need to ask ourselves, can the right boundary of this previous rectangle shift to our current rectangle? Yes, it can, because our current height is greater than the previous height I've seen so far. So in other words, this right boundary can still be shifted one step to the right. Okay, so therefore, we just need to check if the top of the rectangle is larger, but in this case it's smaller, so it doesn't matter. We can just place the index into the stack like that. So this will be 1. Now we go to the next building of height 6. Now this is where it becomes interesting, because notice that the top of the stack is index 1, and index 1 corresponds to a building of height 7 meters. But our current building is 6 meters, which is shorter than the building that we had previously seen. So what does it mean? It means that the building we previously saw can no longer extend its right boundary anymore, because you see, look at this this second building here. It cannot extend anymore because now the next building is shorter than itself. So therefore, what we need to do is that we will pop this out from the stack. Remove it from the stack. Okay? Because this building can no longer extend its right boundary anymore. And then we will immediately update this right boundary array. So this was index 1, right? Index 1. What we will do is that I will replace index 1 with our current index position, which is 2. So in other words, this tells me that the building at index 1 can extend its right boundary to position 2. So you understand how this works now? Okay, so I pop this out, remove. Now, I continue checking with the next building. The next building is 5 meters. Now, 6 meters is greater than 5 meters. So in other words, this 5 meters building can still extend its right boundary to itself. So this is fine. So in other words, I can just stop the algorithm, place index 2 in. So do you realize that this corresponds to 6 meters? And notice that this stack preserves its monotonic property. So what exactly is a monotonic property? Is that the values inside this stack is in strictly ascending order. Okay, this is 5 meters. At first it was 5 and 7. Then when I see a 6, I remove the 7 and I put the 6 in. Okay, so this stack preserves its monotonic property. And that is very important, because without a monotonic property, you cannot check if a building basically is taller than all the buildings in the stack. Because notice we only check the top of the stack now. Because if it cannot even pass the top of the stack, then it definitely cannot pass the bottom values in the stack. So we don't need to check through every single value in the stack later on. So this is why a monotonic property of a stack is very essential in this algorithm to solve this in ON time. Okay, so now let's go on to the last building. The last building at index 3 is of height 3 meters. So we do the same algorithm. We check if the top of the stack consists of a building that's taller than itself. So yes, it does, right? 6 meters is greater than 3 meters. So in other words, we pop it out from the stack. This is index 2, right? So index 2 is here. I remove it and I put the current index I'm looking at. So removed. Now notice the stack still has another element and is still taller than the current building. So I also have to pop this out. Remove it at index 0, right? Index 0, I replace it as 3 as well, like that. Now the stack is empty. If the stack is empty, there's nothing else you can do. Finally, don't forget, put this building back into the stack. So now the stack only has one element. index 3. And this index 3 also corresponds to height of 3 meters. Okay, now our algorithm is done. But don't forget, if your stack is still non-empty, it means that everything in the stack can have its right boundary extended all the way to the last building. So in other words, now I need to run another while loop, remove everything from the stack, and every single value I replace with the final building, which is 4. Index 4, which is, actually imagine there's another building here, that's index 4. So in other words, if there's anything still left in the stack, it means that that building can be extended all the way to the right. So I will replace it until the stack is empty, pop it out from the stack, replace the element at index 3 with the last element at 4. Now I have a right boundary array. So what does this mean again? Okay, let me repeat. This just means that where can you extend your right boundary till? So for example, remember these are the buildings. Index 0 is the first building. This can extend to position 3, which is here. Okay, then this is the second building. It can extend to position 2 only, which means it's just here. It only can extend here. Now this building 6 can also extend only here. And this building can extend only here. So in other words, okay, this represents the right boundary of the maximum place where you can extend your right boundary till. So now that we have done our right boundary, we need to do the opposite for the left boundary. Okay, I will not explain this in detail because it's actually the same thing, but now you do it in reverse order. Okay, so just now we did from the left to the right. Now we need to do from the right to the left in order to figure out where exactly the left boundary of each building can be shifted to. Okay, so I will not explain this algorithm, but anyway, after you get a left boundary value, some values, then for every building, you have a left boundary, you have a right boundary, you can figure out the width of this building. The width of the largest rectangle you can form comprising of that building. Then you multiply by the height of that building, you will get the largest rectangle that you can form for that particular building. Then you do the same for every single rectangle, you can figure out what is the largest rectangle for any building. Okay, and then you can solve this in O(n) time. So why is O(n) time? It's because to go from left to right is O(n) time. Then we do the reverse from right to left is another O(n) time. Then we go through another O(n) algorithm, another O(n) iteration, okay, to figure out what is the largest rectangle you can form for every building. So that's another O(n), and then the total is O(3n), which is still linear O(n). Okay, so this is a variant of the problem, how to find the largest area of a rectangle, okay, for a given height of a building. Okay, but this is not the problem. Remember, we are still looking at the original problem. The original problem is given a piece of land. What is the largest parameter of a rectangle that you can form? And notice that there's no like height of building in this question, because how do you know exactly where the height of the building is? Because your building can start from any position. So therefore, this question you need to modify your algorithm a little bit. Okay, so what we can do is that we can figure out how to solve this in this order. So let me just teach you how to do this. We need to create our own building before we can run the algorithm. So what we can do is that given a layout like that, you realize that a rectangle can have any base. So what we do is that we go through every single possible bottom as our original base. So for example, the base is here. So we set our base as this base here. So we set this as the floor. Okay, and what we're going to do is that we are going to set up our buildings. So what is the height of the building? Remember, a dot represents is a free square. So we will just represent it as a building. So what we can do is that here, we will keep an array of the height of the buildings, okay, given the current floor. So given this floor, notice that there is no building here, right? So this is 0, height 0. Now there is one building here, it's a height 1. Okay, there is no building here, so it's 0, 0. So basically, we create our buildings, okay, and then we run the algorithm that I said just now, the left boundary, right boundary algorithm, and then we can calculate what is the largest area of a rectangle you can form given this floor. Okay, but the question says what is the largest parameter. So you can just make a slight tweak to the algorithm. That means, right, instead of finding, so remember just now to find area, what we did was to find the right boundary minus the left boundary. This will give you the width of the rectangle, multiplied by the height, right? This will give you the area. But this question is not asking you for area. This question is asking you for parameter. So how do I do that? Parameter, the simple solution is just, it is actually just the 2 times the height plus 2 times the right boundary minus the left boundary. Because for every rectangle, the max that I can shift to the right and shift to the left, the difference is the width of the rectangle. And the height of the rectangle is just the height. So you can just find the parameter by 2 times the width plus 2 times the height. Okay, that's the only difference. So for these buildings, I run this algorithm, find the largest parameter I can form, store it somewhere. Okay, store it as a record. Store it as a record. Now, okay, you shift your floor downwards like that. Because there are many possible floors, so you can shift your floor downwards. Now, how do you update the buildings array? Is that if you see a cross, immediately reset it to 0. So this is a cross, this is array 0, so this is just reset to 0. Now this is a dot. If it's a dot, you add 1 to the original height of the buildings. So this will be 2. And there's a dot here now, so this will be 1. And there's a cross here, reset it to 0. So correct. So this will be, so given this floor, notice that this building is height 0, this building is height 2, this building is height 1, this building is height 0. So we update our buildings, run the algorithm again to find the largest parameter you can form, update the record. Next, we do the exact same thing. You shift our floor down. Okay, shift our floor down. And we update the height of the buildings. So there's a dot here, right? It means that you add 1 here. And there's another dot here. So you see, there's another dot here. So this will be 3. There's a cross here, immediately reset to 0. There's a dot here, add 1. So the height of the building is 1, 3, 0, 1. Notice it's 1, 3, 0. Because this is, you ignore everything that's above it. You just look at what is currently here on the floor. And this is 1. So given this height of the buildings, you run your algorithm again, update the record. Finally, you go to the last floor. Okay, so this is 2, right? This is 2, this is 4, this is 0, this is 0. So this is where we update 2, 4, 0, 0. Okay, run your algorithm again, find the largest parameter you can form, update the record. Finally, your answer will be in the record. Okay, so what is the time complexity of this algorithm? Okay, so let's imagine that this is a square, n by n. Okay, you need to go through n floors, right? Because the floor keeps changing. It can be multiple floors. So you need to go through every single floor. That is On by itself already, to go through every single floor. And within each floor, you need to run the algorithm to find the largest parameter you can form. And that is another O3n. Remember, there's an O3n algorithm. So it's still On. So you have an On loop to go through every single floor. And within each loop, you run an On algorithm to find the largest parameter you can form using the stack algorithm. Okay, the total is On squared. This question can be solved in On squared. The complexity, so let's take a look at the constraints. R and C is the number of rows and columns, is at most 1000 only. 1000 is 10 to the power of 3. So On squared will pass because 10 to the power of 3 squared is actually 10 to the power of 6 operations, which is less than 10 to the power of 8, which is the number of operations you can allow to carry out in 1 second. So the answer, okay, this is the best algorithm you can think of, On squared. Okay, there should not be any other ways to solve this problem. Okay, other ways that you might actually solve this problem is to actually brute force all possible rectangles, and that is too slow. Okay, so using a stack for every single layer, you are able to cut it down to On squared. So that is how you modify the original algorithm, which is to find the largest area among some building, largest rectangular area among some buildings, and we would use it to solve the largest parameter of a rectangle. And we will use it to solve this variant where you do not know where the floor is. So you need to brute force every single possible floor, and then you rerun the algorithm. And then you store the best result that you can find so far. Okay, so that is how you solve this question. It is a bit difficult, okay, but it is very handy to know how to use a stack to find out the largest area of a rectangle you can form. So that's all for this problem.